Good morning, my dear students. Imagine listening to your favorite song. The sound waves travel from the speaker to your ear, but have you ever wondered how fast these waves move through the air? The speed of a wave, called velocity v, connects frequency f, the number of oscillations per second, and wavelength lambda, the distance between two consecutive peaks. The relation is simple: v equals f times lambda. This means that in a given medium, where velocity remains constant, if frequency increases, wavelength decreases proportionally, just like a seesaw. This elegant inverse relationship explains why wave motion is both simple and fascinating, and it applies to all mechanical waves, including sound. Frequency is defined as the number of oscillations or cycles of a wave per second. It is a measure of how fast the source is vibrating. Mathematically, frequency is written as f equals 1 divided by t, where t is the time period of the wave. The C unit of frequency is the hertz, written as Hz, which is equivalent to 1 cycle per second. In sound, a higher frequency corresponds to a higher pitch. Human hearing usually ranges between 20 Hz and 20,000 Hz. Have you ever noticed how you hear a train approaching much earlier when your ear is pressed on the railway track compared to listening through the air? That's because sound doesn't travel the same way in all materials. The speed at which sound propagates depends on the medium's density and elasticity. Generally, sound travels fastest in solids and slowest in gases. The wave speed, denoted by v, is expressed as v equals the square root of e divided by rho. Here, p is the modulus of elasticity and rho is the density of the medium. This explains why in solids, where both elasticity and density are high, sound travels much faster than in air or water. For example, the approximate speed of sound is 343 meters per second in air, 1480 meters per second in water, and as high as 5120 meters per second in iron. Finally, changes in temperature and humidity also affect wave speed in gases because they influence the density and molecular motion of the medium. Have you ever stretched a slinky toy and noticed the repeating loops? The distance between two loops is like the wavelength of a wave. Wavelength, denoted by lambda, is the distance between two consecutive points in phase, for example, two compressions or two crests in a wave. For a sound wave, wavelength relates spatially to the extent of one complete oscillation. It is given by the formula lambda equals v multiplied by t, where t is the time period of the wave. In a sinusoidal wave, wavelength can be measured directly from a displacement time or displacement position graph. And importantly, wavelength is inversely proportional to frequency when velocity is constant. This means that as frequency increases, wavelength decreases, keeping the product constant. Let's solve a quick example to see how the wave formula works in practice. We are given frequency f equals 512 Hz and wavelength lambda equals 0.67 meters. We need to find the wave velocity v using the wave equation v equals f multiplied by lambda. Now substitute the values v equals 512 multiplied by 0.67, which equals 343.04 meters per second. Thus, the speed of sound we calculate here matches the typical value of sound in air at room temperature. This confirms that our answer is reasonable. Let's quickly wrap up what we've learned about wave velocity and frequency. The important formulas are v equals f multiplied by lambda, f equals 1 divided by t, and v equals square root of e divided by rho. In a given medium, the wave speed is constant. This means frequency and wavelength are inversely related. Remember, frequency depends only on the source and is not changed by the medium. Wavelength, however, varies with the medium and is always inversely proportional to frequency.